Welcome everyone, friends of open source FPGA stuff and other good fun here to our FPGA series. And of course we have the microphone cable below it. Anyway, also the latest version of Qt OBS Studio and uses next PNR just updated yesterday on T2. What could possibly go wrong? Anyway, wish me luck. So what I initially wanted to do, actually clear from Jose's next PNR iStorm and FPGA general infrastructure fun notified me on Twitter that she has a new RISC-V core in the works. It's not yet, it's alpha or beta, not yet like for general consumption, but if I wouldn't want to try it out, and so this was already 3 or 4 months ago, yeah, like probably nearly 5 months ago, and only these days I finally found the time to give it a try. So what this is, so I didn't talk that much with her. I guess she's also a little bit busy. Maybe we should resort to some good old-fashioned voice call some other day, but as far as I understood, and I only have here a tiny little overview, this is supposed to be when it's, well, right now it works. I tested this here on the Jülich 3S, but for me it's not yet any benefits, but it's supposed to be more generic. So I guess it probably maybe already supports 64-bit instead of previously PicoRV only 32-bit. And optionally pipelined and stuff. But right now I tested this, so it works. I can show you how to plug it into another PicoSoc example project that was relatively tiny. But I wanted to show you some other things. So just initially I wanted to make a video like, hey, it's amazing and 4 times the performance, but unfortunately in my testing it wasn't yet faster. And because it's lacking right now hardware multiply divide and what else? Something else that I'm not using that. So what I'm still using today, and I wanted to show you, is here's a previous product of ours, RX32, our homebrew microprocessor system. This also from her is a PicoRV 32, the otherwise nice little performing Pico RISC-V core, and we were running this already previously, which we have here running on the serial console, and some many months ago, like 5 months or something, I also implemented this Game of Life here, which we can run here, of course, and I thought the performance might not yet be totally ideal and amazing, and certainly for our stuff it should be ideal and amazing, and I wanted to make this a little bit faster. And this is also why I wanted to plug in this new RISC-V core in there, and it wasn't faster yet. So while working on this and benchmarking this a little bit more, I noticed that, or remembered that we are running from Flash. So all this code here, which is also why it's not reaching top performance, is running from the serial Flash. This is also what this, from the PicoSoc example project, this stuff here is switched to default mode. So this default dual, quad and double data rate and continuous read modes are for the serial Flash here. This is again from the original firmware, and I can show you the speed difference here when we say 3 and run this, and yeah, this is the default mode, like how fast is serial SPI Flash, yeah, that fast. And then of course when we switch to dual I/O mode, it is certainly nearly twice as fast, and same then for quad and double data rate. You probably get the idea. And then also continuous read mode allows, as far as I remember, to address once and continue reading from like the same like auto incremented address, saving some addressing latency at the beginning. So with this, so far I even changed our RX32 firmware a long time ago, like half a year ago, to default to quad DDR mode, I guess maybe without continuous read mode, but probably we also want this, and with this is already relatively fast. And then I thought, wait a minute, why don't we, like another day, we certainly need to implement some like real cache, because we have here fast SRAM, what you would usually build cache out of. And certainly there are many examples out there. So if you want this today, you can just go to all the open hardware sites and plug in there some cache for some improved speed up. But for today, I wanted to YOLO this here a little bit and wanted to show you how I've done this. All right, I should have actually restarted Emacs for you to better read it. So much too. If you're wondering why I usually have this terminal stuff so large, then here it's RXVT. YouTube and Emacs init for high DPI. What was it, 12 or 20 or what did I even hit there? Must be some. Is it even the right file? Init. Also Emacs for those playing along at home. And probably that triggers some people because VI. So either 20 or yeah. So let's comment out my YouTube line here, which probably is that. PicoRV 32, and some of the stuff is already upstream there in the GitHub repository of ours. And if you are very interested in exactly this system with the ULX3S or Icebreaker, leave me in the comments below if you want to see more work on that. But otherwise, I also have a couple of other things to do, which is only why I only work sometimes on this stuff. Let's see, yeah, that's probably large enough for you playing along at home. And so two things. So the first thing is, if you want to work on Claire's new PicoRV CPU, then plugging it into there, so you just git clone this. Obviously you run make -C source generate to generate this code because it can be parameterized and is generated out of Python, as far as I remember. And then you get a file picorv.v for Verilog. And just to show you, if you wanted to play with that, because it doesn't yet have much documentation, then plugging it into your existing PicoSoc project is super simple. Took me only a tiny little trial and error, and I have it even in here. So this is a PicoRV, how you instantiate the current existing years old PicoRV 32. The Verilog module instance here, CPU with clocks reset n, and here's some parameters. And this is a new one, so this would be PicoRV easy, I guess. Here are some different, you see the parameters are completely different. This is like cycles per instruction something. So 1 should be a 4-stage pipeline, and 2 should be like half, like 2 clocks per instruction or so, not pipelined. This is new, the XLAN. If you watched my previous RISCV ISA instructions architecture video, XLAN is the instruction set, the ISA document name for the instruction length, as in 32 versus 64-bit. I've not tried this, but I guess either now or sometime soon you can instantiate it then with 64-bit if you wanted a 64-bit RISCV CPU in your FPGA design. And then what also I only found out with chatting with Claire regarding the compressed instruction set extension, which previously was .compressed either, you can enable, because first I thought this compressed extension is not there, but no, it is there. It's enabled with instruction align 16 versus 32, and if you instantiate it with 16, then it's compressed. And spoiler alert, for me this didn't yield the highest FPGA synthesis performance, so with this I achieved this design achieved much lower clock frequencies for some strange reason. So I right now this synthesizes with some 48 megahertz. We are running at 42.5 I think, but it's next PNR tells me it's good for 48 megahertz, which we do not run because my SDRAM controller can't reach double data rate of that, but previous video. But anyway, if we enable instruction align 16 for compressed instruction extension, then it is significantly slower, only reaches some 38 megahertz or something, so 10 megahertz slower. Then some naming here is slightly different, but yeah, previously CLK is no clock, but reset is previously, this was reset, not now it's reset, so we invert that. And that's nearly everything. Why do I even talk about this? You could say, yeah, YOLO, whatever, not a big deal. There are two more things. The first thing is you see here is the the stack address, so this is used for reset when you like your real silicon that you purchase from Intel or someone else, Motorola and stuff. If you enable power supply power to your integrated circuit, and it has certainly some built-in predefined reset address, some reset vector that starts executing, and you can, this being a soft core in Verilog and FPGA, you can configure this. And for the program reset, this is still here, but for the stack address, which we also need because the stack address needs to be in SRAM and not in like ROM, because it wouldn't be writable. We need some stack address, and this doesn't have a config parameter anymore. And I had to look this up and read the source. So here, reading the source, it turned out this is done in assembly startup language now. Also not the right file, probably. Kill this buffer, yes, please. The firmware, start, what did I open here? Start.s, no. Comparing this, so this is, reading the source. And I got this from reading Claire's new example, icebreaker example for the new PicoRV. So with this is, we just do it in assembly now. Previously this was all 0 here, and now it is, this is a previous stack address. Theoretically I could make this nicer and somehow YOLO this from the makefile some parameter. But yeah, stack address here defined for exactly that. Stack address here to this 32 bits of zeros plus 4 times the memory words, which are 32k. So 32k multiplied by 4 and then some space for whatever. Not entirely sure for what, but doesn't matter much. Anyway, so this was the first gotcha. So much to hear. You have another soft core, some details may vary. And another thing, so this still didn't work. Another thing is Claire has changed. It took me also like 30 minutes or so, because this I would get here this starting up message, but it would still not work. And after further comparison, it turned out Claire has changed this instructions here. So previously this was read cycle and read instruction. I wanted to research, I've not yet researched. Maybe this is an unofficial extension, not really entirely sure. Maybe that is not standard conforming. And the new core, this is why I now have here this defines. Previously this ASM assembly volatile inline assembly code was spread over the whole file of the example firmware with read cycle and read instruction. And the new is CS, is whatever that stands for. Actually googled it the other day. I should have actually opened it. RISCV ISA PDF, some custom like model specific register read. Let's check exactly. Oops. CSSR CSRRS. There it is. Read instruction, retired counter and cycle counter. So yeah, read, what does it stand for? This is some pseudo instructions are accessing control. So this is control and status registers, obviously. So read, control, status register, read. So I guess, hey, it also has a read time clock. Amazing. So while we have this document open, we could actually check. So this is, previously this was hanging. Maybe it was firing an interrupt. Didn't really further investigate what the new core would do when it encounters in instructions that it doesn't support. x86 or other processor would, of course, throw some non-maskable interrupt kind of exception vector of illegal instruction. We could actually read cycle. Do we have this? Here's also read cycle counter. Okay, this is interesting. This should maybe x0, whatever. Anyway, it didn't work for whatever reason. probably need to check what is different in the encoding. Anyway, so yeah, these are the two things, the bigger of course being the stack pointer. And with that, comparing it back and forth with the performance, I was thinking, how can we somehow get our precious game of life running from SRAM, right? Because certainly we don't, even with the fastest quad double data rate, I can also show you this SPI quad DDR. Probably we get hopefully some nice diagram for that. And in previous videos, as seen in previous videos, SPI is by default only one wire, and these 4 wires are optional. So this is some like dual and quad optional higher performance wiring, and then you obviously read this twice, 4 times or 8 times as fast, and certainly that greatly helps performance, as you can imagine. But even if in the fastest flash mode, serial flash mode, we certainly don't want to read everything from the serial flash mode. Certainly SRAM can only be faster than that. And again, ideally we want some proper cache for that, and we could even cache that from the ROM theoretically, but that's for another day. So this is our function, and I figured I fiddled around, so this is probably the best solution, and took me also, so you see how much time all this takes thinking about playing around with it. Could have done it live on YouTube. Leave in the comments below if in the future I should. Because what I came up with is actually pretty neat. So we attribute this, so this is general GCC or other compiler extension for, like, as you see, inlining. Here we also have attribute always inline. I added this also for exactly this case. And here's our live run function. And this function I attribute here now to a custom section fast code. And again, previously in earlier tries, so the first actually spent an hour on this amazing optimization. And initially I wanted to copy the code, like relocate it, like it's in the third megabyte of our EEPROM. Third megabyte because the first is the bit stream. So when you turn this on, the FPGA will load the bit stream of its internal logic element configuration, the FPGA bit stream here out of the serial ROM and the serial flash. And after this is why our code lives after the bit stream. So right now happens to be it's a third megabyte because the freaking bit stream is 3 megabyte. And so initially I wanted to custom copy this, like think memcopy, just like we have our variables here. And actually this reminds me, do we run this right now from SDRAM? Yeah. And so similar to this, I wanted to make here just a normal variable, like say some 200 bytes, check with object dump or some linker trickery how large our function is, because fun fact, in Portable C you can't even get the size of your function, because, and that's not something you can query, or actually even the compiler knows, or it's of any use in working with C. So YOLOing that, like wiring this up in whatever way and custom copy this from 3 megabyte ROM address to fast SRAM memory. And by fiddling around with this, there are some, for this to work, actually we would need to make sure that it doesn't have any, well, all the code is inlined, because if a lot of this code here is calling into other functions, like the functions implementing the evolution here, so we live evolve here for 1 generation. And this is why previously here were jumps obviously to this other functions. And if we want to custom copy this to a faster cached memory, obviously all this code needs to be together in one block. And this is why I attributed all the stuff that we are calling there always inline here, because otherwise we optimize for size and it wouldn't inline this. So this is why here are now some always inline to tell the compiler, hey, please pretty always inline this. here live add and live draw and live evolve. And then while I was fiddling around with copying this, I figured why not let the linker do this stuff, because from Claire we have here already some trickery actually in the startup code. And this startup code is already copying here somewhere, worker begin, it is copying the variables, because they certainly should live in the memory. The variables, if they would be all in the 3 megabyte of ROM area, we could never modify them. So this is why this linker script already had here data. Initialization of the data section, program executes knowing that the data is in the RAM, but the loader puts these initial values in the flash init data. It is one of the tasks of the startup to copy the initial values from flash to RAM. So that is what this stuff is doing, and I added here fast code. So all this stuff was already here from the PicoSoc project we inherited, and I added here fast code asterisk for fast cached code to be copied to SRAM 2. And lo and behold, this really worked. So this was all what is needed. So much to custom copying the stuff around, which certainly is not amazing and not very reliable and portable. And because what this is also doing is, if we would custom copy this, I came to this solution because any of these jumps here, the problem is with copying this yourself, like having a pointer, like C being C, you have a pointer to everything and can shoot yourself in the foot with that. And the problem is that even if we would custom copy this ourselves, this live run here, any of these calls, or not even calls, any of these variable references must be absolute addresses, because the linker right now, you see placed it here at the 3rd megabyte, and this would certainly not work if it's addressing, like relative addressing stuff, not only for calls but also for variables and other stuff. So while I was evaluating this, thinking about if this would work or not, again, by the way, these are the compressed instructions here, then I thought, can we not get the linker to do this? And indeed that works. So section fast code, let's comment this in here, and let's make that again ulx3s proc. And with this modification, flashing takes a tiny little amount of time, obviously here 16%, there's no other input, because this is loading this. It's actually not flashing this, flashing would be even slower. This is loading this with a loader directly into the FPGA, so like basically bootstrapping this via the USB cable, of not going for testing purposes via the flash. So yeah, shortly loading this. Unfortunately, it's not the largest delay, but it certainly teaches you to always think about what you're doing before synthesizing and flashing all this stuff. So now, as you see, this runs even faster, and I had here outputted the number of, similar to the short benchmark here, which is that cycles. So this came already from Claire's PicoSoc, cycles instructions of this number 9 run simplistic benchmark. The problem is that this counter overflows. And so now we have L for game of life and capital L for the thing with benchmark. And unfortunately, it certainly is faster, but this counter overflows. So instruction also pretty many, even just a little bit of perspective, even this tiny little demo of filling the memory, like also counting. So you see how in the real world, how many instruction cycles all this code takes, basically hundred thousands, if not millions, of, because counting all the fields of not the highest optimized, but yet loading like plenty of load instructions. We count here for this game of life, we count here the surrounding neighbors, so we count like probably 8. I guess either all 9 or probably 8. Would need to check this. So plenty of memory accesses then writing this to new memory locations, then drawing this. So basically we use text mode, so this is already highly optimized. As you see, we have a graphic mode, but this is running in text mode for performance reasons, because then we have only 2 or 4, actually we have 4, it's basically 32-bit per. Actually, did I optimize this? Probably I should check if I have optimized that. Yeah, 216 characters, color, attribute, and text glyph. Obviously we just fill there a full ASCII block. But so this is text mode just for performance, because if we would fill graphic pixels, it would take even more cycles filling the whole 16 by 16 square, unless we graphic asteroid that. But yeah, for this little tiny thing, millions of instructions, probably next I probably should add a real timer that we can better time this. But yeah, it's just like 1 second for this 100 iterations. And theoretically, we could also check. Right now, for testing purposes, we run this out of SDRAM, because I wanted to stress test our SDRAM controller. Probably it should also be faster if we, I don't even remember this, I've not done this today or yesterday, but instead of SDRAM live state, we could probably comment out that and name this state. Probably should be enough. And then this is a regular variable instead of our external SDRAM high memory. Let's see if this just works. It should theoretically be even faster. And one funny thing is, one last little note, that each time you run this, the number of cycles of instruction clock cycles is another one. If you run the benchmark, probably this simplistic benchmark was reproducible stable number, but most likely because we have so much I/O access, so basically we bit bang like massively our video memory also, which is probably why we always have another amount of wait states for the VGA VRAM to catch up. Yeah, can also disappear again. So let's see, does it look faster? Maybe it's already plenty fast, but yeah, certainly. What do we get here? Be something. Yeah, I probably next need a better timer. Probably instruction. By the way, it's instruction count. Actually, the funny thing is, even the instruction count is not very stable. F8. I mean, it's F8 something. I slightly wonder why the instruction count. All right. Maybe could it be that, depending on the. But actually, the initial state should be the same. Anyway, this is slightly interesting. So can we disappear here? Anyway, so that is that. If you want to highly optimize this, then certainly run your stuff from SRAM. Maybe implement a cache or relocate this. Other fun stuff. Of course, other stuff here still works. Fun fact here of our SDRAM loading stuff. Also, this is just some text output. All the previous videos, including MIDI and audio and kind of pseudo beeping FM synthesis, all the plenty many FPGA videos. If you want to see more of this, leave in the comments below what interests you the most. Should we maybe advance this further to have this here fully working gameable? Maybe I should actually write Tetris and Pac-Man next. But yeah, just some ideas. And another thing is, maybe I should next change this example. So certainly some other small hanging fruits for you playing along at home would be here. So what I would improve next is I copied here from Claire's firmware, example firmware, this structure of test commands here with one button press. Obviously it gets a little bit out of hand with this test commands. So certainly one low-hanging fruit would be to make this here more shell-like and not accept here one character but a whole string for enter, and put all the stuff here in a table of like a C array of commands to run. That certainly would clean up here and makes this much more usable. Also, yeah, more like firmware-like of sync SGI ARCs or PowerPC Open Firmware stuff, if you would want to use this for a real project. And then the other thing that's certainly a totally easy thing that every one of you could do if you wanted to and send a patch. Another thing, maybe the next most useful thing, would be to change this code here to move this more sophisticated examples like MIDI playback, audio playback, to programs like freestanding programs if we wanted a RISC-V microprocessor platform, like standardized Commander RX32, and change this, not that these example programs are all in this one ELF or binary raw program, but change this so that all the sophisticated stuff are freestanding ELF, like, what is it, extended link, what was it, format or something. Just looked it up, ELF, Unix, Wikipedia here of executable in link format, I was close. Like RISC-V ELF, maybe potentially like converted, either we could write a loader to load like a firmware load RISC-V. Leave in the comments below what you think, or alternatively, the much easier thing would be to pre-process this stuff, the executables, to a fixed address, similar to our firmware, so that it's raw binary files similar to DOS COM executables, all the previous videos where we did this for Virgin Voodoo and did low-level hardware-isolated programming on DOS. So like have a COM, actually, you know what, we could actually support both, right? So we could make this like .com, just for the sake of it, have this similar to this firmware here, that would be here in the make file, of converting this to from ELF to bin, like this object dump here, object copy binary, this here, and have here COM binaries, or maybe we could call it X, whatever, does totally not matter. But maybe I do this next, trying to load raw programs from the SD card, so that would be the benefit, that we could distribute this, like we would have a well-defined platform and could have programs on the SD card for you to load and share, like Pac-Man and Tetris and audio stuff and other fun stuff. And yeah, leave in the comments below what you think, what you would like to see. Theoretically also, certainly maybe basic, but maybe something more performant and programmable like Lua. Just some ideas, but it's mostly there. Another thing is what I probably should do really probably soon, like aka next, is actually keyboard input, because right now it's of course only somewhat nice to always have it here on a USB terminal, but yeah, keyboard certainly in the USB port, yeah, for you playing along at home and plugging into a TV and actually playing this stuff, RISC-V stuff. Anyway, theoretically I would be a little bit interested what the real performance is here of this core. This is counter overflowing, that's the most helpful. So anyway, for the real for a real microprocessor homebrew system, we certainly need a timer next, and interrupt handling, and so that you can time stuff nicely, like frame animations and sound and MIDI and audio output, and also do freaking better benchmarks. Let's see, do we have this RISC-V stuff? So they had here timer. What would be the time base be? Read timer encounter. So that would be pseudo instruction counts volt clock real time that has passed from the restart time in the past. Anyway, we actually have a real-time clock on this thing, and was here even, yeah, there is even you probably don't see this with this lightning, there's even space for a battery on this cool Ulix 3S. Probably we should actually support this. Here's a battery. Maybe I should actually get a battery and plug one in there. Some CR1225. That probably would be a very good idea. Anyway, that's it what I have for you today. I hope you enjoyed this and learned something. As usual, leave me in the comments below what you like to see most, what you would find the most useful, or what other comments you have. I hope you learn something from this experience going through all this stuff. Designing this is similar to how you would develop a firmware, if it's a wireless access point or industrial control, motor engine control, ECU, industrial control, you name it. And I hope you learned something. Probably also another day we need to modernize this. It's already compiling as C++, you know, from maybe our IT news that we are not the greatest fan of C anymore. This is a little bit ironic that we do this here in C for you to get started, but yeah, certainly something. Anyway, hope to see you soon. For the next videos, don't forget to share, like and subscribe. Maybe send it to your friends and family who might be interested in this kind of low-level IT stuff, programmable field arrays, and in case you're wondering, we also do otherwise fun little vintage Unix stuff here. So Octane is standing for a reason. Octane coming. Plenty of videos, and sometime soon, because we finished some precious bootable Linux stuff there for MIP64. But that's for another day, and I hope you tune in for that as well.